welcome back for the second video. I'm going to try to make this one a little bit quicker. So we're going to look at our second scenario where we have to compare the means of two groups. So this one's going to be along the lines of where we have two independent groups, possibly from random sampling. So we're going to use the t-test, and we're going to use the technology to run this hypothesis test. So this is our first problem with matched paired data, where we had meaningful pairs of the specimens of the data for each specimen. So now we have this scenario where it's a medical scenario. So it says cholesterol level above 250 milligrams per deciliter of blood is a risk factor for cardiovascular disease in humans. A medical center in St. Louis studied the effectiveness of new cholesterol lowering drug versus a standard cholesterol reducing drug. They said they have 100 people right here. They have 100 people with cholesterol levels between 250 and 300 milligrams per deciliter. They were available for the study. It says 50 people were assigned at random to each of the two treatment groups. One group received the standard cholesterol lowering medication, and the other group received the new drug. After taking the drug for 3 weeks, the 50 subjects who received the standard treatment had a mean decrease in cholesterol level of 10 milligrams per deciliter with the standard deviation of 8 milligrams per deciliter, and the 50 subjects who received the new drug had a mean decrease in the 18 with a mean decrease of 18 milligrams per deciliter with the standard deviation of 12 milligrams per deciliter. Does the new drug appear to be more effective than the standard treatment in lowering cholesterol levels? So give appropriate statistical evidence to support your conclusion. Whenever we see that, this statement right here, give appropriate statistical evidence to support your conclusion, we're talking about a hypothesis test. So to understand this, you have two groups, which can be regarded as subsets of two different populations. A population of people who have taken the standard cholesterol lowering medication, and the other one would be regarded as 50 people, regarded as a subset or a sample from a second population who receives the new drug. So that is what we're trying to compare: is what are the effects? What would the effects be? How would they be different if a population took the standard cholesterol versus the new drug for reducing cholesterol? All right. So here's our setup for this. We have first things. What are our parameters that we are interested in? Our parameters are our population. We have two populations we're talking about. One population is a group of people who take the standard cholesterol reducing medication. So one parameter of interest to us is the mean decrease in cholesterol level for the standard group. And the other population we're interested in is the new drug group, and we're interested in the mean decrease in cholesterol level for the new drug group. So you can imagine having two very large populations who are prescribed these medications, and they check in for cholesterol level. The 50 people in each group can be regarded as a sample of each of those populations. So we are going to compare two populations, and we have two samples, have a sample from each. Okay? So we have our parameters of interest, our hypotheses. So when you go into this experiment, if you are the scientist, what's your expectation? Your expectation is that, if they're both valid cholesterol reducing drugs, you would expect them to do about the same, right? So you would expect that the difference in their average reduction or decrease should be about 0. In other words, the mean reduction or mean decrease for the standard group should be equal to the mean decrease in the new drug group. What's the alternative explanation? What are we worried about here? Does the new drug appear to be more effective? So this part's important, to be more effective than the standard treatment. So what does that mean for our hypotheses? Well, that means that if we take this difference, standard minus the new, we should have a negative difference. That means that in general, the new drug over here, on average, will produce a greater reduction in cholesterol or decrease in cholesterol level than group 1. Okay, so that's why it says greater than. Even though we're talking about a decrease in level, we're talking about how much does it decrease. You would want a better drug would decrease the cholesterol level higher average. So those are our hypotheses. Someone asked me this earlier today in an email. What if I don't have a significance level? Then you make your own up. So part of running these sort of tests and running these experiments in the real world is you set your own significance level. So we are doing this test at the 5% level. 5 got cut off. So alpha is going to be 0.05. So we have everything set up, our parameters defined, hypotheses defined. So the next thing is, we got to check conditions. So we have information about two samples or two groups. At this point, we're talking about means, so that's telling us we're probably going to need to use some sort of t-test. But since we have two separate groups, two independent groups, we're probably going to be looking at what's called a two-sample t-test. And to use a two-sample t-test, we have to check some conditions. And we learned what those conditions were for the means. And so what are they? The first part, do we have any randomness going on? Yeah, we do. We don't have a random sample. The 100 people were available. It goes back to, we talked about this earlier in the year. How could you force anyone into the study? You can't. So they were volunteers, but they were random. But 50 participants were randomly assigned to each group. So you have random assignment to each group. You must say that you did this for each group. Okay. Both sizes of the groups are 50. That is larger than 30. So we can use the central limit theorem. The central limit theorem applies. What does that mean? That means that the sampling distributions of these means, the averages we're going to get from our sample here, from these two samples in a second, the difference in those sample means is going to be roughly normal, which is important. We need them. We need to have a larger sample size here. So we can apply the central limit theorem. We don't know if the populations of cholesterol levels are normal, so we have to start here and we think, okay, we're good. Sample size is at least 30, so we have the central limit theorem, and we can use a normal distribution, or in this case, like a t-distribution, which resembles the normal distribution. Okay, number 3, we have no reason to believe that anyone's cholesterol level in these groups would influence others. The 50 cholesterol levels in each group are independent. There's no reason to believe that. If you're working at a medical center, there's no reason to believe that anybody's cholesterol is dependent upon anybody else's. And then finally, the standard deviations of the cholesterol levels in the populations of people who receive the standard drug and the people who receive the new drug are unknown. So that means that sigma 1 and sigma 2 are unknown, and this allows us to use a two-sample t-test for the difference in these two means. So we can use a two-sample t-test, and at this point, we will use our calculator and kind of run some statistics for it. So here's what we have. So we're going to enter this data into our calculator. Let's get some sample data from our problem. The sample data for the standard drug group, what we said, we had a mean decrease of 18 milligrams per deciliter with a standard deviation of 12. That was for the new drug, and the standard drug had right here 10 milligram average decrease and a standard deviation of 10 or 8 milligrams. So our sample data for x bar 1 for referring to the standard drug, that had a 10 milligram or milliliter decrease, milligram decrease per deciliter, and the standard deviation for that was 8. So this is 8. N1 was 50. Sample 2, which refers to our new drug group, this group had a mean decrease of 18 and a standard deviation of 12. So if you just look at the numbers, the new drug had 8 milligrams per deciliter more of a decrease than the standard drug. But they were also more variable, so that's something to consider too. That a higher standard deviation. So we need to think now, like, is this difference we see here significant enough? So let's go in here. We got sample 2. Its size is 50. Okay, the statistic we use to calculate this thing, what we're actually interested in, is what is the difference in sample means, and what does that tell us about the population? So this is really 10 minus 18. We observed a negative 8 milligram per deciliter difference between our samples. So the question is negative 8, this difference, going to be significant or not? And to answer that question, we have to finish our hypothesis test. So we're going to use the technology to do this. So remember, we assume that there is no difference, so we get a difference of 8, negative 8. And we want to know, is that enough to make our conclusion? So let's take a peek here. You go to your calculator. So you're going to go to your stat, calc, tests. Okay, so now you have a 2-sample t-test. That is going to be number 4. So we pick number 4. It says input your data or statistics. We have statistics. Okay, x bar 1, that was 10. Standard deviation of that first group was 8. This was 50. Sample size was 50 in each, the group size. This was 18 for group 2. Standard deviation was 12. This is 50. For means, okay, what was our alternative? Our alternative was that the mean for group 1, which is the standard group, the mean reduction would be less than the mean reduction by group 2, so we're going to pick this one. We don't do pooled here. We're not going to do pooled. And then we come down and we hit calculate. And we notice that this gives us a few things. It gives you your test statistic, gives your p-value, gives your degrees of freedom. So we need those things right there. So take a quick little snapshot of that and transfer that over. So we need this for our analysis, and this should finish up our hypothesis test in a second. So we have our test statistic, which is negative 3.922. P-value, it is not 8.8. It is 8.8 times 10 to the negative 5th power. And degrees of freedom is 85.37. So your calculator does the calculation for degrees of freedom for you using a fancy formula that we don't have to worry about for our purposes. So what do we say for our conclusion? So our p-value, according to this, change this over to green. According to our data we have, our p-value is equal to 0.0000884. That is what 8.8 times 10 to the negative 5th is. That is clearly less than our significance level 0.05, which means we reject the null hypothesis that there is no difference in mean reduction between the groups. That means we have evidence, the data, the evidence, the data we have suggest that the new drug group has a larger decrease or average decrease in cholesterol level. Okay, so just to sum all that up, what does that mean? That means that this 18 is far enough away from 10 to say that, you know, these two drugs do not work at the same rate. This drug 2, the new drug, probably reduces cholesterol level at a higher rate. So this difference we saw of -8 is far enough away from 0, it's rare, it has a low probability of occurring, that we can reject this idea that this hypothesis right here is actually true. In favor of this one right here, where it appears that on average the new drug reduces the cholesterol level a little bit more. So that's our conclusion. The last thing here, this is your test statistic for this. You don't have to write this, but this is how it's calculated. This is how the t-score is calculated right here. It is x bar 1 minus x bar 2 minus 0, because that's the expected difference, over the standard error. And these are some formulas you can find on your formula sheet to help reference that. So the standard error of the difference in the sample means is right here. That's how you calculate this. So you could substitute these numbers in to verify that for yourself if you want. But this is your hypothesis test for the difference in two population means.